One of the uses of the integral is to compute the area under the curve, and in this section we're going to do it explicitly using the rectangles or familiar shapes that we know about, just to get a feel how to actually compute the area under the curve, and then we will use the integral or the idea, the concept of the integral to compute the area under the curve a little bit later. So first let's explore the idea of using rectangles, a number of rectangles on an interval a to b, for example. We'll start with 4 rectangles. Now there's a number of ways you can do this. You can have the rectangles touch the curve at the left endpoint, right endpoint, or midpoint. And I think I have shown, and maybe I will show a little link showing the different ways to have the approximate area under the curve. So first of all, here I have a little picture, so to speak, if you can imagine. So if we think of the width of each rectangle as delta x, or change in x, that's where the dx is coming from. And the way we can compute it, we can take the length of the whole interval, which is b minus a, and then divide by number of rectangles. So it should make sense. So we'll have b minus a over n. And then you have also number of endpoints. So you actually always have one more endpoint than the number of rectangles, because you start with the a, then you keep adding the width of each rectangle, so you'll get x1, x2, x3, for example, if you have 4 rectangles, and b would be x4, but total you have 5 points actually. So what happens is, if you're touching at the left endpoint, then how we're going to compute the area, if you recall, the area of the rectangle is length times width. But instead of multiplying each length of each rectangle by the width, what we're going to do is we're going to add up the lengths and then multiply it by the width at the very end. So sort of like factored out version. So if we have delta x times, if you're touching at the left endpoint, so notice the first rectangle is touching at a precisely. So we have f of a plus the next one's touching at x1. So it would be f of x1. The next one is at f of x2, and the last one is at f of x3. Notice the last one, b, doesn't really play a role here for the left endpoints. So we do have 4 rectangles. And how you compute the y's, the f, you either can plug into the function, or you may be given a table or some other way to compute it. So to do it with the right endpoint, it's a similar idea. So notice the difference, but then we start with f of x1 because we're touching at the right now, then f of x2, then f of x3, then plus f of x4, which happens to be f of b. So notice for the left endpoint, you start with a and you end up with 1 just short of b. And with the right endpoint, you start with x1, the next endpoint, and then you are finished with b, and that's how you know. So these sums are usually approximations. It just depends on the curve whether it's over approximated or under approximate. You notice with the rectangles, some of them come outside the curve, so they over approximated. Some come under the curve, so they under approximated. That's why using 4 rectangles, it's going to be a very crude approximation. You want more of them. In fact, integral uses infinitely many of them, so you get really good approximation in that case. Or I think the limit as n goes to infinity. Now the midpoint is usually a little bit better, because if you're touching at the midpoint, notice not as many rectangles over or under approximate. So what you're going to do is you still have your 4 endpoints, but then you're going to find the midpoint of between each of them. I didn't write it out, but later in the example I'll show you how to do that. So let me kind of show you this applet. See if I can maybe click on this, and let's see if I can do the link and show you guys. Let me see, it uses Java, so let me try to run this. Okay, so if you click on that link back there, notice how you can use the right endpoint, and you can use the slider just to show yourself. The more rectangles, the better the approximation. Notice at about 40, looks like it's very good approximation already, but you can keep on going. And notice you get area under the curve as that's what the integral is doing actually. You're taking as many of them as you can. So delta x or dx is going to 0. And that's where it's coming from in the integral. Then you can click on the left endpoint. Let me see if I can move the window a little bit to show you guys. You can click on the left endpoint. Let me show you fewer of them. So this one is where the area is touching at 4. Notice with 4 rectangles, it's pretty obvious. But then you can do fewer of them, and notice you're getting better approximation. Let me show you the midpoint. Midpoint is a little more accurate. Notice already with like 10 of them, you get a pretty good approximation already. And of course, like at 20, that's already very good. So if you have like, let's say, few of them, notice how you just have each rectangle touching at the midpoint. Okay, so this is just an example using, let me see if I can get back to our notes. So we can change the number of rectangles, and basically I show you guys. So how do we calculate it? Well, each time, if you know how many rectangles you're going to use, let's say 4, then you're given the interval, so you can compute the delta x, which is the b minus a, so it's 2 minus negative 2 divided by 4, so it happens to be 1. It's nice when it's an integer. I drew the picture. You don't really have to draw it, but it really helps to visualize it first. So the left sum would be area equals to the width, which is 1, that's delta x, times, start with f of negative 2. Now notice negative 2 is touching the x-axis, so the first rectangle is actually going to have length of 0, which can happen. So it's really under approximating. So we have f of negative 2. Then you can keep adding width of 1 until you reach 2. So you'll have negative 2 plus 1, you'll get negative 1 as the next one. That's how come I drew it. So f of negative 1 is the second rectangle. Then 0, because if you add 1, you'll get 0. So the third rectangle is touching the curve at x equals 0. And the fourth rectangle is touching at 1. So notice we don't quite reach 2, the last endpoint. So we have, so all the y values will have 0 plus 3 plus 4 plus 3. So we add them up and you get 10. Okay, now the right sum, I try to draw it also. In this case, sorry, let me go back to the picture. In this case, notice how we start with negative 1, that's where it's touching the curve, then 0, then 1, and then the last one at 2, which is 0 again. So notice, I think the sum is exactly the same, 10, which happens because the picture is symmetrical. And then part C is asking to find the average between results A and B, and that's just average like in statistics. So we add them up, divide them by 2, so you still get 10 because of the symmetry. And midpoint sum, what I did was I kind of drew them, but notice each midpoint is right in the middle between the two endpoints. So the first one is negative 1.5, the next one is negative 0.5, then 0.5, then 1.5. And I plug them in, and the easiest way to do it is to graph it and use the table feature on the calculator if you don't want to do them each individually. And that's what I think I did. I graphed x squared, negative x squared plus 2 or plus 4, sorry, and then use the table. So I get 11. So notice it's a slightly different value, maybe a better approximation you get for the area. And then I did the same thing with e to the x minus 1. Here I really used the table feature. Notice how I used decimals here. The left sum happened to be 27.19, and that's what I actually said to use the table. The right sum happens to be much larger because you don't start at the 0, but you actually start at the next one, and you end up with f of 4, which is a much larger value. So notice sometimes the values differ very much, especially if the function like e to the x, which increases very quickly. Then the average happens to be 53.99. Again, I added them up, divided by 2. And the midpoint sum, again, I just took the midpoint of each interval. I got 0.5, 1.5, 2.5, 3.5. That was from 0 to 4, I believe. And I got a better approximation, which is 47.43. Okay. And that's kind of the idea. The rest of the section, which I'll try to go show you guys, is what if the area under the curve. We'll continue with this next time. On this next section, we'll use actual integral idea. But in this case, what if the shape is like of the shape of the known a geometrical form like a circle, triangle, etc. We can find area using geometry. So there's going to be a few problems in your homework. Let's say find area using different areas like circle, triangle, and so on. So notice here's the graph is given. For example, I tried my best to draw it. And notice how it looks like a rectangle from 0 to 2, and then from 2 to 6 it looks like a quarter of a circle. So the area of a rectangle is just the height times width, which is 4 times 2, and that was 8. Fourth of a circle, well, the full circle would have been pi r squared. Fourth of it is 1/4 pi r squared. How did I get radius to be 4? Well, notice from 2 to 6 you get 4, or from 0 to 4 on the y-axis you'll also get 4. So I got 1/4 times 16, which is 4 pi. So the area was, I think both of them, combined area was 8 plus 4 pi. Okay, then we can do the same thing with, let's say, the first half. It doesn't really look like a circle, but it's still a quarter of a circle. And then the second part is a triangle. So it's 1/4 times pi times 2 squared. So 2 happened to be the radius. Plus the area of a triangle is 1/2 times base times height. So it was 1/2. The height, I think, was 2, and the base was 4. I think I got it backwards. Base times, oh, that's the same thing. Okay, so I got pi plus 4, or 4 plus pi. It's either way is fine. And what if you have an actual integral? We don't know how to integrate this directly, actually, but you can graph this on your graphing calculator, and you can figure out if you put x minimum as -4 and x maximum as 0, you'll see it's quarter of a circle again. I don't think I drew it, but it is a circle. X squared plus y squared equals 16, with radius equals 4. So this is the window I used. So you can actually use the x min as the endpoints of the integral. The y mins, I just played with them and I noticed that it was 4, so I changed it, but you can always change that. So quarter of a circle is 1/4 times pi times 4 squared, which was 16. So to gets you 4 pi is the answer. Or here is a little bit more challenging one, but it's kind of same idea. So the integral is area under the curve. So what if the function is 1 plus 2x, which is a line? The way how I got the endpoints to draw the picture, I plugged in 2 into the line. So I got 1 plus 2 times 2, which is 5. So, no, 4, sorry. 1 plus 4, I get 5. That's how come the first point is 2, 5. And then if you plug in 5, I get 1 plus 10, which is 11. That's how come I got the y value. So I drew the line, and then I just kind of drew the little dotted lines up all the way down to the x-axis, because integral is area under the x-axis. And notice again we get a rectangle and a triangle, and you can combine them. So I got the rectangle was the 5 times 3. It's not really drawn to scale, but it's base times height, 5 times 3, so length times width. And then a triangle was 1/2 times 3 was the base and 6 was the height. And so I get 15 plus 9, which is 24. And applications, here's a quick one. Usually the y values are provided either via graph, chart, or a table, and the idea is exactly the same. So let's say the speed of a particle in a test laboratory was noted every 3 seconds. The results are shown in the following table, and use the left endpoints and then right endpoints to estimate the total distance for the particle moved in the first 3 seconds. So here we have the times, 0, 1, 2, 3, and then we have the velocity, which is in feet per second. So you can guess that the interval in the first 3 seconds would be from 0 to 3. That's how come I got the width of each rectangle was 3 minus 0 over 3, which is 1. Okay. So then the left sum, basically, you take the 1, which is width of each rectangle, times velocity at 0 seconds, velocity at 1 second, velocity at 2 seconds. So I got those y values of the table, added them up, and I got 22.5 feet. So notice the area has the concept is distance now. So we're actually finding the distance because it's 1 second times all these velocities added up. So it's 1 second times feet per second. That's how come we got feet. So area in this case represents distance. So area under the curve can represent different things besides just the area itself. Same thing you can do with the right sum. I got 1 times the velocity at 1 second and velocity at 2 seconds and velocity at 3 seconds. Again, going back to the table, I added up 6.5 plus 6 plus 5.5, and I got a smaller distance. I got 18 feet. So again, depending on which one you use, you may get different answers, but it's still distance and it still has the same idea. So that's it for this section, is area under the curve.